And thank you so much for the invitation. It's a great pleasure to be here. So I'm going to be talking about some new work that I've been doing. This has been an ongoing large collaboration with a lot of different people that I'd like to recognize. The two main people who have done the bulk of this work have been my postdoc, Brenda Benecourt, and then a postdoc that visited my group last year, Giacomo Zanella, who's a postdoc now with Igor Prunster at Bocconi University. A large part of this work wouldn't have been done without Jeff Miller, who is now at Harvard Biostats, and Hannah Wallach at Microsoft Research, as well as a PhD student at Duke, Abbas Zadi. So what I'm going to talk about is some sort of motivations to the data, and then I'll get into, well, what is microclustering, what is record linkage, or entity resolution. But I want to start off with some motivations into how I started thinking about these problems. So record linkage or entity resolution or deduplication is where you have large data sets, and they tend to have duplicated records across them within them. And they occur in all kinds of data sets. So for example, here's an official statistics data set, and this is thought to have been one of the first drawings of an official statistics data set, and this was done by Bruno De Finetti. And so this picture was given to me by one of my collaborators from Italy, Brunero Liceo. And so what it's illustrating is from ESTAT, which is one of the official statistics units in Italy, of showing one of what's thought to be one of the earliest drawings of how the postal service, the telephone systems are working together in terms of unofficial statistics in Italy. So how you're seeing at a very high level duplication happening, and how you would think to try and understand how these different databases might work together and how problems here might arise. And so we still have these issues and problems today. So in our own country, we have, for many years, we've had a large problem in terms of estimation problems with the US census, and these arise for duplications of administrative records. So how do we cope with these problems? How do we improve these problems with our own administrative records, and how do other countries deal with these types of problems? Another large problem, precision medicine. So sepsis is currently a $3 trillion problem. So this article is written by Suchi Surya. So how do we deal with different types of problems that are arising in the original data? Specifically, there's duplicated information within the electronic healthcare system. So this is a problem that I work on related to sepsis, which is patient deterioration. How do we remove duplicated information and records that isn't just static, it's moving over time? So how do we deal with this in a systematic fashion? And this is not just an important problem, but a very timely problem and a very expensive problem. And then another timely, important problem, a very different problem, is in the ongoing Syrian conflict. There are human rights organizations and groups that are collecting information regarding individuals that have died over the Syrian conflict. And as you might think of, as they collect this information, duplication happens, and it's duplication about individuals that have died. So how do we remove this duplication of dead victims or individuals in order to come up with an accurate death estimate? So how do we solve these types of very difficult, timely problems that also have public policy implications? So the common themes of the data that I've just described are they have duplicated data and they're dealing with record linkage problems. So in the picture I'm describing, it's very simplistic here, so I'm just representing two individuals that here are exactly duplicated, where the other individuals that are in white are simply just singleton entries. And so you could imagine this picture changing such that you have more duplication occurring. So how do we systematically scalably remove such duplication to answer interesting questions that are arising from the data? So again, as I mentioned, record linkage is trying to remove this duplication in systematic ways where we have noise in these databases. So one popular approach to solving record linkage is to treat it as a clustering task. And so in this aspect, we're taking records that are similar in some way and we're clustering them. And so I'll get into details of this more. And so specifically, we might decide to cluster similar records to a latent entity. So the idea is that there's some true latent state, and any records that are similar in such way, we're going to cluster them to their true latent state. And of course, this latent state is unknown. So we could try and link them using a data structure. And so what might that data structure look like? And I'll show you a picture of that in a moment. And so I'm going to think of this data structure, though, as being a prior over the set of matches or non-matches, meaning that if I'm taking the records that I'm linking them all together to a latent entity, then that would be the set of links. And so one interesting question that comes up here is, what should this prior over this data structure be? So what are priors that make sense, and what are priors that don't make sense?
Before you go on that section, so the kind of problem I was thinking about, particularly talking about the stereo depth, is that I'm imagining a database or some kind of thing where each record is a piece of a longer, maybe a temporal series of records.
Mm-hmm.
And when you have duplicates, they're not really duplicates. They're pieces of what should be the same record, but pieces at different points in time which need to be concatenated. In other words, the problem of saying that duplicates and you want to remove one of them is a special case of a more general case where the two need to be reconciled and created and converted into a third record, which composes in some way. So, for example, if the third axis was time, you say this happened here, and something happened with the same entity over there. So you merge the two into a third record.
So I'm going to get into an example now of what I mean in an example, in terms of what this looks like in terms of the structural, and I'll tell you about the assumptions that I'm making, and then maybe chime in if...
Yeah, because thinking about clustering seems a bit limiting in the sense that clustering requires that the entities are directly, it's the same or different or whatever.
I disagree that it seems limiting, but chime in if you still have a question. So I'm thinking about, in terms of a westernized example, this particular type of a framework. So this is just a simplistic example. So I have 3 large databases, and I'm thinking about representing each entity as a node. So here I'm just representing each node as a person's name, but it could be different. And each person has different attributes associated with them. So here, Larry Wasserman, he has an occupation, he has a name, he has an address, he has 2 cats, he has a favorite color. And then I'm wanting to figure out, okay, given that I have these attributes associated with each person, I want to know who's the same and who's not the same given this information. So what I'm going to want to do is, in classical record linkage, what people tend to do is they would do all-to-all comparisons, which we know is computationally intractable. So what I'm wanting to do here is, if these 2 Steve Feinbergs are the same, I'm going to represent this with a link here. And if these 2 Steve Feinbergs are not the same here, I'm going to remove that edge here, where the E and the I with the Feinbergs has been flipped. And so I'm assuming that I can have duplication within a list and across all of the lists. So I'm assuming general duplication here. So just, again, as an example of what something could look like in terms of the feature attributes that go along with an individual, I could be looking at a Steve Feinberg that has this particular address, has an age range, and has a particular phone number, and all of this information is available on the white pages. And then I could be looking at another Steve Feinberg that has another address, has a top-coded age range, and has a different phone number. And so you want any type of method that you build or algorithm to be able to tell the difference, for example, that these 2 Steve Feinbergs, even though they live very close to each other, to be able to say that these aren't the same, and you want to be able to do this to say this scalably over the set of all records. So what I'm thinking about here is doing something where I'm clustering records that are similar. So here the Steve Feinbergs to a latent entity or individual, where the latent is completely irrelevant. So it could be an S, it could be a Steve, it could be a number, it could be anything. And I'm going to keep doing this. And I'm doing this over a generative mechanism or model. And then I'm going to do it again. So when I was at Carnegie Mellon, I had a colleague, Ryan Tibshirani. He often gets confused with his father, Rob Tibshirani. So how do you separate out individuals that have similar attributes and names? So I want to cluster all the Ryan Tibshiranis to the same latent entity R. And hopefully, I want to be able to tease out any Rob Tibshiranis from that association. So here's what it would look like for the Syrian conflict. It's going to look exactly the same and very similar. So here I'm just showing 3 of the human rights data sources. We actually have 4, but we're still just clustering similar records to latent attributes, and we're doing the clustering. So here we're just showing the non-westernized version. Okay, so what have we done in the previous work before I get into the microclustering? Yes? Yes, yeah, exactly. So yeah, let me clarify. Great question. So here, these are representing different data sources where the data sources are collecting information about individuals who have died over the conflict. So this source is collecting information. And so there's duplication across, so within and across the different databases. So here I'm simply listing the Arabic name. We also have date of death. We have a high-level location, as well as a gender of the individual. And so what I'm doing here is I'm saying, okay, well, these individuals are clustered to this latent entity 1. And so I'm simply just putting the node as the actual individual, and I'm wanting to remove the duplicated individuals that have died. Yeah. So I'll get into that in a second, but yes, we treat the duplicates within a source different than across. And so the reason that we're doing that is so that we can capture the record linkage uncertainty so that we can actually, so if we look at the entire space here of entity resolution as a whole in terms of what I think about this as being deduplication and this actually being record linkage when I go across. If I look at that as a whole in terms of the entire graphical modeling process, then I can actually look at the amount of record linkage uncertainty for the whole process. And then suppose I want to know the death count, assuming that for the whole population, then I can take that record linkage uncertainty and put it into a capture-recapture model to actually try and estimate how many people have died, assuming not just for the sample, but for the entire population. Or I could do anything for any type of other inference I might want to know about. So suppose I want to know I'd like to do something with a logistic regression or just a regression. I can take the record linkage uncertainty, which I know exactly from this model, and I can propagate that into any existing analysis. Yeah?
So while we're asking the question, does your prior try to generate the names and addresses, or is it somehow conditioned on the names and addresses?
The prior on these models right here, which I'll get into, is taking a very, it is not, the prior on the actual data structure is a very simplistic prior, which is not taking into any information on the names and addresses. And those were previous papers that were not addressed in the NIPS paper. And that might be a good question to come back to at the end of kind of what we're doing in future work.
It's just you gave the example before about how the two Steve Feinbergs are clearly not the same because their names are spelled a little differently and they have different addresses and phone numbers and ages.
What we are doing, so let me jump to this slide and and then I'll show you what we're doing. So what we are doing is we're using a distance metric, which is taking into account the similarity or dissimilarity between names given any distance metric.
Got it. Okay, so the prior is conditioned on the information about individuals.
Yeah, and I'm happy to talk to you offline if you want to know more about this particular model.
Okay, no, that's fine.
Yeah, sure. So in these particular sets of papers, what we tried to do is the previous literature wasn't balanced on many things. So it wasn't balanced regarding modeling, handling high-dimensional data, as well as the uncertainty of handling multiple databases. And so what we did is we built a Bayesian model that's a generative model that's doing simultaneous record linkage as well as deduplication. So that's the step that I was talking about on the previous slide. We're assuming the records are noisy in some way, so we're handling a type of model distortion. We also have a representation which was novel to this work, which we call a linkage structure, which is taking into account the sets of edges and non-edges, which allows us to move through the space quite efficiently in terms of when we look at a Markov chain Monte Carlo. So we have a hybrid MCMC right here. And so the real strength of looking at the Bayesian approach here is that we're also, since we're able to look at this as a bipartite graph, we're able to get transitive closures almost trivially. So by a transitive closure, what I mean is that if I have a record A that matches to record B, and B matches to record C, then I want to maintain the fact that A is going to match to C. And so we're able to do this not just for 3 different records, but for K different records, because we're handling K different databases and we're handling the deduplication and the record linkage all at once. And then the last thing that I mentioned as well is we're able to provide the uncertainty estimate of the record linkage process exactly, which is really nice if you want to then answer some question beyond just record linkage, such as putting that into some sort of logistic regression, or what's of interest to me a lot of times is capture-recapture. So what this talk is mostly about is what should the actual prior on the links and non-links be. And I'm claiming that it shouldn't be something like a Dirichlet process in general, or some type of richer get richer process. And so I'll go through explaining the intuition behind that. And this ends up raising a lot of deep and interesting questions about certain high-dimensional clustering tasks, not just for record linkage, but also for things like community detection, or when you have really small clusters. And so before delving into this, I want to talk about clustering for Bayesian methods a little bit in general, and specifically for Bayesian nonparametrics. So in Bayesian nonparametrics, your goal is here I'm going to just talk about the clustering mechanism, because this part's quite important. So here what we're wanting to do is we want to cluster some number of n data points into k clusters. And so typically, this is quite easy to do. So you take some sort of generative process, maybe like the Chinese restaurant process or the Dirichlet process, and you get some sort of nice separation. And so just as a trivial procedure, here there are 41 data points, and here we get separation into 3 clusters. So typically in Bayesian nonparametrics, we'll want to place some sort of prior over the partitions, which I'll define to be bracket n, which go from 1 to 1n. And C sub n I'm going to define to be a random partition of bracket n. So C sub n is going to be represented by a set of cluster assignments, which I'll denote to be Z1 to Zn. And these are known as clusters or classes or blocks of the partition. So here we simply just have 3 clusters or 3 blocks. And so in a simple example, these could be represented by cat, dog, and mouse. And in terms of the random partition, they could be broken up into the sets of the different data points that we have, where the cluster sizes respectively here for this trivial example are 10, 15, and 16. So many clustering tasks that have been proposed and that have been used in the literature assume the cluster sizes are growing linearly with the size of the data set. So they're wanting this richer get richer process where you keep adding more. As the data set is growing, then the latent size of each cluster is growing linearly compared to that. And classic examples are the Dirichlet process, the Pitman process, the Kingman paint box. And you tend to get more and more behavior like this as the number of data points is growing. You're going to get larger and larger clusters, and you get, with the concentration parameter, for example, on the Chinese restaurant process, it's the sociability parameter or the popularity parameter, and so it's encouraging more people to go into that particular class. And so if we think about that and compare that to record linkage, that is the opposite of what we really want here. We have, if we think about the data set of what we have a lot of singleton clusters. We have very few people that are the same, and we don't want a richer get richer process. We want something that's going to induce small clusters. So how can we do that? And what's really going on with the data? Well, as the number of data points is growing, intuitively, the size of each latent cluster should not be growing linearly with the size of the data set. In fact, it should be growing negligibly to the size of the data set. And in fact, you can show it's growing sublinearly. So just as a trivial example, so my mom and I actually have the same name, but different initials. So it's often a common problem in terms of separation, in terms of my own data. And so here what you really care about is, again, getting these clusters that are really small. We also care about the exchangeability of the data points, right? The exchangeability of the data points here is very important. And so how do we start to think about theoretical justifications as well as proper generative models that will elicit such behavior? Yes?
But do you care about exchangeability because you have domain knowledge that says that there was an exchangeable process generating this, or is it just for computational convenience?
Well, we care about exchangeability, right? Because if I exchange, so if I run my chain for a really long time, or if I think about just 2 data points in the process, if I switch them, then that's a very important point in terms of those data points being distinguishable from each other, if I want to do proper inference. Because if I think about the end goal, I'm wanting to answer some question about the data set, and if I don't have exchangeability of the data points, then it's going to be very difficult to do proper inference about the particular data set.
So I think your answer is that it's a computational convenience.
Exactly.
Yeah, okay. I understand. When you said we care about it, I thought maybe there was some modeling reason that you care. You can always have a non-exchangeable process and then marginalize over the other. It's just expensive.
This is very expensive. So the way that we decided to define the microclustering property is in the following way. So a sequence of random partitions, C sub n, will say just exhibits the microclustering property if m sub n, which is going to be the size of the largest cluster, is OPN, meaning that m sub n over n is going to 0 almost surely. So then we say a clustering model that we define will exhibit the microclustering property if it satisfies this definition that we have stated. So this is something that we had defined in a workshop paper last year. And so we started thinking about, so here we're giving the sublinear behavior. And so I'm going to set out a few models to try and convince you about the generative models that we've laid out, that where one of them in particular satisfies this particular property. And so we've proved this in the paper that will appear at NIPS, and then I'll show you some results from this particular paper of how how we link this then with inference.
Just a notation question in case people don't know this. I want to make sure I understand it myself. So this is little o of n, and the p is in expectation under a probability distribution.
Right. So all I'm saying is that
that's the little o from computer science. It's not something you can find on another slide.
no, it's the little o from computer science. It's the same also in probability theory. Yeah. I was just going to write it out if there was a question, but yeah.
I think people know.
It won't be on another slide. Yeah. So I'm going to show just a few slides of the motivation for the models, the generative models that we came up with, because I think this is important in terms of how we came up with these. So this is a motivational example from that Hannah had from campaign finance data of looking at 100,000 records. And so a lot of the data that we tend to look at, if we think of the ordering of the cluster sizes, they don't matter. And so if I'm thinking about, so here I have the cluster sizes, and then I'm looking at the number of entities in each cluster size or bin. But the ordering, so we're assuming exchangeability, so the ordering doesn't actually matter. And so I can get different types. So here we have this is on the log scale. So we have, out here we have a cluster size that has just one individual. And as we looked at different data sets, we looked at different empirical distributions of the data that had very different types of empirical distributions. And so as we looked at things like this, it was very important for us to capture the true empirical distribution of the data. And so our first thought was, okay, can the Chinese restaurant process recover this for any alpha? And the answer is no. So here we looked at it for one particular value of alpha. We looked at it for more of these. So here we're looking at the 95th, the 50th, and the 5th percentiles. And so here we're just trying to recreate the histogram. And so you'll notice as it's going out, it's not able to catch things in the tail. And so is that surprising? So what we did is we looked at generating the Chinese restaurant behavior for here. We looked at n increasing, and we fixed a particular value of alpha. So here we looked at n varying going up to size 10,000, and you see that basically the distribution that's induced by the Chinese restaurant process is just flattening out. So you're never going to be able to get distributions that are having big tails out with cluster sizes out here. So what happens when we then vary n and alpha together? So basically in this situation, we're varying n and alpha together, as we can see up here. So first we looked at n equals 50 and alpha is 63, and then kept increasing them. And you can see as we move along that we quickly just lose the flexibility of the distribution. So specifically in this plot here, you can see that it's just collapsing down on a one parameter family. And that happens also when you look, for example, at the Pitman-Ure distribution, for when you're trying to look at data of this form. because you have a lot of different, if you think about these as being different parameters, you're wanting to have a very flexible type of distribution that you're trying to fit here. So these are the types of simulations that were motivating the models to try and incorporate the microclustering property. So let me switch to a bit of a theoretical type of framework of, so if we think of mixture models, then no mixture model can actually exhibit the microclustering property unless its parameters are actually allowed to vary with n. And if we think to Kingman's paint box theorem, then this will imply that any infinitely exchangeable partition of n, so of the natural numbers, is equal, it's going to be either equal to the trivial partition, and in that situation, each part will just contain one element, or it's going to have to satisfy the fact that the lim nth, as n goes off to infinity, of the maximum cluster size over n has to be greater than 0 with positive probability.
And again, n sub n is the largest cluster size.
Yes. So then if we turn to Kolmorov's extension theorem, if we think about the sequence of random partitions that we have, which is C sub n, this is going to correspond to an exchangeable random partition in two situations. So either each random partition is exchangeable, or the sequence is consistent in distribution. So specifically here, I mean projective. So in order to obtain a non-trivial model that exists the microclustering property, by Kolmorov's extension theorem, we have to sacrifice either A or B. And exchangeability here is very important, as I stated before. And so what we're sacrificing here is consistency in distribution, or rather projectivity. Hannah Wallach, Lee Dicker, Shane Jensen, and Catherine Heller looked at sacrificing consistency in distribution in a NIPS paper in 2010 over uniform priors. So a slightly different scenario, but also for clustering. But they have no exchangeability, and so this really messes up the inference. Okay, so now I'd like to get into the models. So just a little bit of notation. So K is going to be the potential number of clusters. N sub K is going to be the size of the kth cluster. N is going to be the total number of data points. So for any application, we will know this. And then Z sub n is going to be the cluster assignment of each nth data point.
Let's go back to both the results here. So first, like Finite theorem. Go back to it for a moment. What's damning about it is that, no, one more. Yeah. So what is damning about it is it says that at least the biggest duplicate its size has to grow with that. In other words, it has to grow linearly or more than linearly. And that's what that says, that there's at least one cluster of its size can grow. And I guess that's already bad because you know that in your problem, it's not like there is one entity who's going to keep showing up with duplicates as you add more and more records. You fact that everyone will have a few duplicates, but the number of duplicates is not going to grow with your data size. So I think that's bad enough. But going forward to the next one, the Kolmogorov. I'm trying to think whether this is an equally damning result or it's still workable. And I'm trying to think about its implication for your problem. And I know you're saying you're going to give up on consistency.
So I'm not saying in practice, I'm not making the claim that we shouldn't, I'm not stating that we shouldn't strive to have, I fully believe that our model should be consistent in distribution and projective. I'm just saying that in this certain situation, you need to either give up projectivity or exchangeability. And I'm saying that for this specific type of problem and application, exchangeability, at least in my point of view, is more important here than consistency. And the reason I'm saying that is because, and this doesn't, I'm not trying to say, you still need to do model checking to make sure that your inferences are valid. And that's incredibly important. And that's something that needs to be, that we have thought about and addressed in our application to make sure that you're getting to the right place, because you are giving up productivity. I'm just saying you can't.
Productivity is what that one.
Projectivity is right. Yes, exactly. I'm just saying you can't have both here. And so we thought very carefully about, if you can't have both and you can only have one, then which one should you have?
Yeah, I'm also it's been a long time since I was here, so I'm trying to figure out how bad the inconsistency would be, because if it were a slowly drifting inconsistency, I could still live with it. And I still wouldn't consider the back one. Seeing it as your n grows, you're not consistent with some endpoint far less than n, but you're close enough in some sense to n minus 1.
Right.
So that's okay.
I mean, you can think that, so if I understand it,
Yeah, maybe we can discuss it at the end, because I think it's, so I will say that there are two things that we were asked to do in our rebuttal. We were asked to prove the microclustering property, and we were asked to do a full discussion of projectivity and the exchangeability. And so we added in a full discussion of the projectivity and the consistency, because to us we thought it was a bit obvious, but it clearly wasn't to some of the reviewers. And so we added in a pretty lengthy discussion of that. And it is a very important point, and not something that should just be brushed over. So maybe we can come back to that in the Q&A, because I think it's something worth talking about, and I think it's something that should be carefully thought about. Okay, so we've defined this to be flexible models for microclustering. These, so we're defining this in a very general framework. We're going to let k come from some distribution kappa, and n1 to nk given k be IID from k. So remember k is the number of clusters, and n sub k is the size of the kth cluster. And so all we've done is we've removed a cluster of size 0. So we simply truncated everything. So n is going to be the total number, is going to be the sum of the total size of the clusters. And then given the size of the clusters, what we're going to do is we're going to generate a set of cluster assignments. So these are the z's. And then we're going to draw these, the way that we're going to generate these is we're going to draw these from a vector uniformly at random from this set of permutations. So we'll have the 1's n1 times, the 2 n2 times, and the k's k times. And the reason that we're doing this is for a few reasons. So we'd like to have something akin to a receding algorithm. So note here that we have a model and not a process. So we don't actually have something exactly like the Chinese restaurant process, but we will have something akin to a receding algorithm. And it's nice because the marginal distribution of the random partition can be worked out in closed form when we do this. And that's how we're able to get something akin to a receding algorithm. There are computational burdens from doing something like this. We have incredible computational burdens. We have a new proposal method, which I'm happy to talk about at the end, for addressing this, which speeds up things greatly. And it's not just a one-off of a hybrid MCMC. It's very different. So the first model that I'll talk about that falls under this framework is called the NB&B model. And kind of just one thing that I'll point out is that these models in general can be, the conditional distribution of them can be written as what are called Kolkin partition models or Gibbs partition models. And they have a very specific form. Some of them, if you write them one way, can end up being, so for example, the Dirichlet process can be written as a Kolkin partition model, whereas if you write them in a other way, the way that we have, they can be written in a different generative process to satisfy the microclustering property. And so we realized this after the NIPS rebuttal process, and so we're unifying a lot of this framework. But it's nice that they all fall under the same framework. So the first model is where we assume the cluster sizes come from a negative binomial with two parameters here. And the first two parameters are assumed to be known. And then for the cluster sizes, we're going to take these as well from a negative binomial, where then we're going to draw these from gamma and beta priors. And so we're going to call this resulting marginal distribution of the random partition a negative binomial, or an NB&B model. So if I think of a special case of this, I could have a Poisson with an alpha and a Poisson with a lambda. And that would just be a special case here. So what does this look like, and how does this compare to the Chinese restaurant process? So for the CRP, the receding algorithm, just to refresh your memory, if I have n different elements and I want to reassign an element n, so if I have an existing cluster, or for example a table, then if I reassign this element to an existing table, then the probability is going to be proportional to the cardinality of the cluster size. And then if I reassign it to a new cluster, the probability is going to be proportional to the popularity parameter or the concentration parameter alpha. And so here's the richer get richer process. And so here we compare this to the NB&B model. So here, the existing cluster part is pretty similar, so it's just the cardinality of C plus a constant. But then the difference here is coming from the non-get richer behavior, which is coming in here. And so what's going on here? So the main difference here is the assignment of a new cluster is depending on the cardinality of the random partition, and then I'm taking away the element that I'm currently looking at, that data point n. And that crucially depends on k. And so being able to see that this satisfies the microclustering property is a non-trivial point, and the proof of this is 3 pages and in the appendix of our NIPS paper, which is on arXiv. And hopefully you'll believe me on this point that it does, in fact, grow sublinearly and satisfy the microclustering property. For the Poisson, you get a proportionality of 1. And so hopefully I can convince you there in that special case example that it is not growing linearly.
Okay, so qualitatively the idea is the more existing tables there are, the more likely you are to start a new table.
Yes. Yeah. So in the second model, what we wanted to do is we thought about, as we were running the experiments, well, the negative binomial over the cluster sizes k may not actually be sufficiently flexible for microclustering. And so we were thinking about this as we were writing the paper and also building it. So if we think about in the case where k is very large, the negative binomial won't be flexible enough to fit, for example, k observations, and hopefully this is quite intuitive, and the reason is it's also a 2-parameter family. And so how do you actually build a fully non-parametric model to fix this issue? And it actually ends up being quite simple. So k doesn't have an issue, so still allow this to be a negative binomial, and then allow n1 to nk given k to have some probability mu, where mu is then going to come from an infinite dimensional Dirichlet. So this Dirichlet is going to have a concentration parameter alpha and a base measure mu. So the whole idea here in practice is with the base measure mu, these are actually modeling your actual cluster sizes here. And so it's actually able to fit that flexible family. And so the receding algorithm for what we call the MBD model is very similar and akin to the MBNB model.
So just to be clear, when you say Dirichlet, this is actually DP because it's over the integers?
Mm-hmm. So I think the next natural question is how does one do inference? So in real-world clustering tasks, we have data points x1 to xn, and the total number of data points are observed. So for a simple application, we'll assume the data is of the form x and L, where n is indexing how many records we actually observe, and L is indexing the features within a record. So for example, something like date of birth, something like gender, etc. And so here we're going to assume categorical data just to test out how the method is working. So here this is simply just putting the entire method together in terms of the clustering and the inference. So here C is just simply a function that's mapping the random partition and a particular record to its latent cluster assignment Zn. So Cn can come, the random partition can come from any model that falls in the FMM framework. And then Zn just comes from this particular mapping. And then in terms of the generation process from the data likelihood, we're simply here just assuming it comes from a multinomial Dirichlet, just for simplicity. This could have any form that your data would adhere to, or this would come from looking at specific applications. So we're assuming the base measure here on the Dirichlet is assumed to be known, and we're taking a flat concentration parameter. So in terms of the experiments, what we wanted to look at is looking at this for 3 real examples. So one on medical data, one on official statistics data, and then 2 different partitions taken from the Syrian data. And to look at comparisons on how these compare to the Dirichlet process, the Pitman process, and look at many different summary metrics on how they actually compare, to try and build a general method that works for 3 very different data sets. So we assessed how each model fits on some summary statistics, looking at quantiles, singletons, etc. We also looked at the estimated cluster size, false negative rate, so precision recall, things of that nature. So the first data set is official statistics data that comes from Italy. So it's survey data from 2 different years in Italy where 74% of the data are singletons. There's unique IDs that come from something that they have there that's akin to social security number. There's also a sample that was taken from the National Long-Term Care Survey. So this is a survey about older Americans. It's longitudinal, so there's 3 different waves where patients drop out or they die in certain waves, and then they're replaced by a new cohort. This is completely categorical. There's date of birth, there's gender, there's an office location, and the state in which they lived in. And it's been anonymized for privacy reasons. In the 2 different other data sets, these are 2 samples from the Syrian conflict that had been anonymized. So they include all of the information from the Syrian data set except for the Arabic name. And so we don't expect this to work well on this data set because we've removed the most information that we have about the data set. So ground truth is known for all of the above data sets on some level. So we compare this using what we knew on these particular unique IDs. So Here what we're looking at is for the Italy data, so we're looking at the singleton clusters here, then we're looking at the maximum cluster size, the mean cluster size, and then the 90th percentile. So what I'm looking at on the x-axis is I'm varying that concentration parameter that I fixed. And in yellow here, I'm looking at the Dirichlet process. In blue, I'm looking at the Pitman-Yor. In red, I'm looking at the NB&B. And in teal, I'm looking at the NBD. And so I'm looking at those for the 3 different versions as I varied the concentration parameter. And so here, what I'm looking at in gray is I have the ground truth under the unique ID. So here we can see that the NB&B and the NBD are getting closer into the number of singleton clusters for as I varied that concentration parameter that I set to be known. So we get similar behavior for the for the maximum cluster size. So these are harder to see, but we get similar behavior down here. If I look at the mean cluster size, so the ground truth is up here. And so the NB&B and the NBD are also getting closer to the true value up there. And so the takeaway here was that the NBD is doing slightly better than the NB&B, which is doing slightly better than the Pitman-Yor, which is doing slightly better than the DP. This was the same conclusion on the medical data. And so given the fact that the NBD is more flexible than the NB&B, and these are more flexible than the Pitman-Yor and the DP, this wasn't surprising for these data sets. These data sets, the unique IDs are thought to be incredibly accurate. And so these results weren't too surprising. We also got similar results in terms of the recall and the precision and those types of summary metrics. So then we come to the Syrian data set. So remember here, we have very little information to match on. So here, there's no clear winner. This isn't very surprising for a lot of reasons. So again, we have very little information to match on. Also, it's thought that the hand-matched data has some problems in terms of, is this line correctly accurate? Is there biases in it? How would you correct for that? And so it's not completely clear how you would choose a winner from this data set at this time point. And so we're talking more with the human rights group about the training data and the problems regarding the training data. And I'm happy to talk more about that. But in terms of these results, there wasn't a clear winner in terms of looking at all the summary metrics for the Syrian data sets. The difference between the Syrian data sets is the Syria sizes was looking at both deduplication and record linkage, so it had a maximum cluster size of 10, whereas the Syria 2000 data set was more realistic of a straight deduplication data set. So the goal was to try and see if the method had issues with deduplication versus deduplication and record linkage. So again, the challenges with Syria is matching on very limited information, so specifically just 3 categorical values. As I said before, the training data here is thought to be incredibly noisy. So the empirical distribution function that we have may not be representative of the underlying distribution. And just as a takeaway, the flexible microclustering models, they tend to do better or just as well as the infinitely exchangeable models on these types of data sets. So where are we going from here? So we expect these types of models that we've proposed on microclustering to beat the Pitman-Yor process and Dirichlet process models as n is increasing. So these were some studies that we looked at on smaller data to get a sense of how do these work on general different types of applications, but we expect these to do even better as n is increasing and as we're scaling these methods. So for scalable microclustering, what we've proposed is a chaperones algorithm. The main idea behind it is that, as I said before, most of the data points you have aren't the same. So you can boost this with a general proposal. So you have in general types of different MCMC algorithms, typically you might do something like a hybrid MCMC where you do a split merge type approach where you uniformly at random propose two records, and then you either split or merge them based on a Metropolis Hastings proposal. For record linkage, that's a terrible idea. And the reason is because most of the records are not the same. So especially in high dimensions, that's going to fail terribly. So what we've proposed instead is a proposal distribution based on two records given the data, where you want this proposal distribution can be any distribution that has positive probability. And the idea is that you want this to induce some measure of similarity. So it's built specifically for where you have something like record linkage. It's also different from the split merge approach because you don't need Metropolis within Gibbs. So you can simply just do a Gibbs sampler. So the implementation of this is, in terms of the details, is in the NIPS paper, but it's a very simple type of approach where you're able to quickly move across different clusters. And so that's how we're able to do the computation of that long vector that is incredibly computationally challenging. There's related work to this in community detection where you're breaking things down into modular clusters. So this is in the networks literature. And so we're looking at potential microclustering models and issues here regarding the data. There's also a package regarding this forthcoming to Korean. And then I'd just like to thank my co-authors because this wouldn't have been possible without them. And finally, I'd like to thank an NSF grant for funding this work, as well as the Human Rights Data Analysis Group out of San Francisco for providing the Syrian data. And I'm happy to answer any questions.
Thanks for this. That's sort of a neat question. So I understand this clustering approach, but we can also, I guess we can also view this duplication as a bipartite matching problem.
Mm-hmm.
And are these the same, or are here differences in what are the differences?
So the way that I view it, there's two answers to the question. Some of the clustering approaches are not bipartite. So for example, this one is bipartite because of the way that you're viewing the graphical structure. So it's the way in which you're combining the clustering with the inference, and you're saying, oh, there's a true latent entity, and I'm taking the records and I'm clustering that to the latent entity. And that creates I think it's easiest to see here, is the bipartite graph. There's many types of clustering approaches that don't induce a bipartite graph. And so that's when you lose things such as transitive closures. And then I'm not saying there's anything wrong with those types of clustering methods, but depending on what types of questions, at least with record linkage, you're trying to answer, transitive closures are incredibly important because if I have, for example, suppose that suppose that the top of the graph is representing Ryan Tibshirani, and this is representing Rob Tibshirani, and then this node is confused, which is why it's connected together, then how do I break apart this particular graphical structure and in a sound way to say that, okay, this is really Ryan and this is Rob. And if you build a sound model, then you can actually break this apart. And our proposed methods allow you to do this. And this simply is just the Bayes estimate.
I'm wondering if it would be easier to deal with microclustering properties of the bipartite.
So when you'll end up, so
For example, if I have prior over bipartite matchings, would it be easier to, or would it make sense to incorporate some sort of microclustering property into that kind of prior as opposed to what you presented here?
in what way?
Do you think that's something like that?
Yeah.
You already want to have both.
Yeah, something like that. So I don't know if it's actually the same thing or not. So say I just have I have a bipartite graph and then I have a prior over the matches. And maybe it can be some prior to enforce that based on microclustering property.
So you're still going to get a bipartite graph. It's just going to be, it's hidden because so I think it's apparent here because here you're seeing it over the linkage structure, which is the lambda. And what we've done is we've hidden it through the random partition C sub n. But you're going to get a bipartite graph. So the way that we've written instead in the NIPS paper is we've written it over the set of all random partitions. And you can still do that with the linkage structure. It's just more awkward. And I can talk to you more offline about what that looks like if that's helpful. It's not obvious. But it's a good question. Yeah.
One of the models that was incorporated this information you have that cluster should not grow too large. I would sacrifice the exchangeability. I was wondering if you compare empirically, like you can still compare like how big the mean size of the cluster becomes if you use something like a distance dependent CRC or anabolic model derivation. So to find that there is any, if those models were not very good in comparison. So like, I mean, other than the fact that you can't compute probability estimates, they can still give you a cluster that was all you wanted. Like, the clustering was all you wanted, like I didn't have and then you wanted to compare like metrics, equals or some other entity clustering metric. You could still do that. So I was wondering if like empirically more or maybe you're in the wrong.
So we didn't check those for the paper. We've looked at them a little bit informally. The main problem with looking at a space over a uniform prior is the fact that it ends up being, while it is uniform, it ends up being incredibly Thule high informative. And so this is something that I looked at in an earlier paper, which is appearing in December in JASA. So it's this paper here. So what it shows is that this is related to Hannah's paper as well. So Hannah and I had many discussions about it. So what happens is if you look at the marginal distribution of the prior that I used of a discrete uniform or the prior that was in Hannah's paper, what happens is suppose this is the ground truth on, let's just call it lambda, or on the true links. So suppose it's here. Then what happens is the prior will put all of its mass over here. And so it's skewing everything in the wrong way. This would be the marginal distribution over the linkage structure. So this, I'm looking at this as a density estimate. So this would be like pi of lambda, and this would just be looking at like this would be on like a discrete measure. So if I'm looking at this for the one of the data sets, suppose the total number of people in it was maybe 10,000.
Binomial AQ for K, and then you had the negative binomial. This is the next one. Yeah, and then, so this was fine, and then AQ, R, and P. And if you go to the next slide where you show the receiving algorithm. Yeah, so how is that data related? Where is that? It must be some function of AQ or P in the receiving probability. You said receiving is proportional to the number of existing clusters minus the one that we have plus A times beta. I'm just trying to figure out how to choose hyperparameters that have some sense for how likely, or ultimately, if I give my hyperparameters A, Q, or P, how does that relate to my data? I mean, I could look at it in paper if it's just some derivation that all the I was just trying to get some intuition about how to choose those four parameters at some point.
So I remember for the gamma and the beta, we took these to be relatively flat priors. For A and Q,
A almost tells you how insensitive the receiving is to the number of clusters. Very large.
Yeah.
Almost always correct.
For A and Q, I don't remember how we chose A and Q, but I can look that up after, and that's something we thought about very carefully, because if you choose that in a very bad manner, then your inferences will be affected by that. We chose them by looking at expectations and variances. I just don't remember the exact equations.
Similarly for the NB,
Mm-hmm.
the base measure is 0. Any guidance on how that's chosen, or do you look at some?
Right, so for the base measure, I believe, so one very simple way you could take them is simply looking at the MLE, the empirical distribution of the data, things like that. One thing we've been doing is looking at actually putting priors on these.
You obviously you prefer having more mass on the ends being small, like 1 and 2.
Exactly, yeah.